get everything set up. And so there are a couple of orders of business to go over at the start. First one being, this is at its core a physics problem, right? And so if we want to, we can use formal language from physics to talk about it. Now, I will do that if it will be beneficial for you guys, and I won't if it won't. So first of all, can I get a quick show of the hand raising emote for those of you who have taken a physics class before? Okay, cool. So a few of you, I will mention things for your guys' benefit. And in addition, can I also then get another quick show of the hand raising emote for those of you who are interested in me going over the math? Okay, cool. Again, a few of you. So that being said, other order is I will be stopping periodically to ask all of you questions. But please, if at any point there's something you don't understand or you want clarified, please feel free to just send a message in chat or unmute yourself and say something. I will be happy to answer any questions at any point. All right, so without further ado, I'm gonna go ahead and get into it. My name is Joel Bernstein. I am a senior astrophysics major at the University of North Carolina. And I want to talk to you guys today a little bit about dark matter. Now, you may have heard somewhere that dark matter is this kind of invisible stuff that we know has to exist, but we've never seen it before, and we can't actually directly detect it. And naturally, this is a pretty weird statement, right? And I definitely was confused by this when I first heard about it. What I would like to do today is kind of demystify this and help you guys understand why it's completely reasonable that we know that this stuff is there, but we can't actually directly detect it quite yet. And so naturally, the first question you'd ask about dark matter is, what is it? And although that's a great question, if you can actually answer this, then there's probably a Nobel Prize waiting for you. So we have to ask a little bit more of a humbling question first, which is, what do we know so far about dark matter? And what we do know so far is that we have a lot of direct evidence from our basic understanding of physics and observations of astrophysical objects like these spiral galaxies. Now, when we look out into the sky, we see many, many, many of these kind of whirlpool-like structures of primarily stars and gas that also contain stuff like black holes and planets around the stars. They look very similar to our Milky Way. And what we can do here is, well, we know stars are really bright, right? Like they light up everything around them. They're very luminous. And so if we can see all this stuff that's lit up by the stars, we can count it all up. And not only can we count it up, we know what it's all made of. And if we know what it's made of, we know how much mass there is. And so we can tally up all of the mass inside of these galaxies. And if we know how much mass there is, then we can figure out how strongly gravity pulls at any point on the galaxy. If we know that, then because of our understanding of physics, we know how fast each part of the galaxy should rotate based on our understanding. And I'm going to walk you guys through how we can figure out all of these things. So to first of all spoil the punchline a little bit, what we expect based on our understanding is something that looks like the left. This is what happens if we simulate the rotation of a galaxy based on our kind of understanding of how much stuff there should be there. What we're going to see is if we plot the speed or the velocity at which stars are rotating around the center on the y-axis, and then if we plot on the x-axis, the distance from the center, so going out far from the center, how fast are they rotating? Well, we can see that the velocity curve that gets plotted here on the left actually ends up being very different from the one on the right. The right being the velocity curve we see if we actually take our telescopes and we point them at galaxies in the sky and observe directly how fast the stars are rotating at any given point. You can see, as opposed to kind of dropping off as you go towards the outer edges of the galaxy, it kind of flattens out, meaning it's rotating at a similar rate, very far away from the edge of the galaxy and some, intermediate distance, not as far away from the center of the galaxy. So to understand how we can make these predictions, first of all, we're going to have to go down to brass tacks on some fundamental properties of physics. The first being gravity. Now, gravity is a force that all objects in the universe experience. Of course, it would be a little bit hard for me to draw all objects in the universe, so I'm just gonna use the example of two little balls here. They all experience a pull towards each other. And this is true for every single thing. Everything you're looking at is pulling on everything else from their inherent gravity. Now, things will always be pulled towards the center of the other objects, right? So this ball, if we move this ball in the right, the pull that both balls experience from gravity are going to move to compensate. So they're always being pulled towards each other's center. And gravity, the force, the value of the force, how strong gravity pulls is affected by two things. If we move these balls closer together, they're going to experience a stronger pull. And now if we also increase the mass of one of the balls, that'll also result in a stronger pull. And now notice that increasing the mass of this ball is equivalent to increasing the mass of the other ball, because both balls need to be pulled by the same amount, right? So if we increase the mass of this ball, then the amount that the right ball is being pulled increases. The amount by the left ball, the amount that the left ball is being pulled by increases by the same amount, right? So if everything is pulling on everything, this begs the question, why is your computer not being pulled towards you, right? If my ceiling fan or my bed or my chair that I'm sitting on is being pulled to me due to gravity, why are they not flying towards me, and why am I not getting hit by all the stuff, right? Well, of course, there's stuff you have to consider, like my fan's kind of bolted into my ceiling, so luckily that keeps me safe. There's friction, right? So anything that's touching another thing is going to be kind of held onto it by friction. However, right, if you throw a ball up into the air, you just kind of see the ball fall right back down to the earth. You don't see it being pulled towards you. And the main reason for that is something, let's see. Exactly. The gravitational force of the earth is way stronger than the gravitational force due to any other object anywhere near us, right? Something on the order of like 70 kilograms. Well, the earth right there, right under us, is I believe 6 septillion kilograms, which is 6 with 24 zeros behind it. Now, nothing even remotely that massive is anywhere near us, anywhere close enough to have a strong effect from gravity compared to the earth, right? And so this leaves one more kind of loose end though, right? Let's say we have a hot air balloon, on orbit a little above the earth. Well, the hot air balloon pulls on the earth and the earth pulls on the hot air balloon. Makes total sense. Now, we understand why the hot air balloon isn't being pulled down. The warmer air within the balloon is less dense than the air around it. So the hot air balloon just naturally experiences a push upwards. That's all fine and dandy. Does anybody want to tell me why then the Earth doesn't move up to meet the hot air balloon? Right. So the Earth is heavy enough that the pull from gravity due to this Earth hot air balloon system is not significant at all. And that's because of its huge mass, just like we were talking about before, right? So if I push on my laptop, you probably just saw it move a little bit. You saw my screen shake, right? But if I were to go out there to my driveway and push on my car with the same force that I was pushing on my laptop with, I probably wouldn't notice it moving at all. And that's just because my car is just so much more massive that push is minuscule to it. It barely cares about it. And so one last potential thing we need to sort out is, let's say we have two people standing on opposite sides of the Earth. Well, these two people, oops, sorry about that. These two people are going to experience the same pull from gravity, but well, we're not entirely sure why that is right now, because they're in two different places. That doesn't exactly make sense, intuitively. The reason, if they can be in two entirely different places and experience the same pull from gravity, is because, well, first of all, the Earth is a sphere, right? If the Earth is a sphere, no matter where you walk, your experience of looking downwards is always looking towards the center of that sphere. And we noticed earlier that the pull from gravity pulls any objects towards each other's center, right? And so downwards for you is always towards the center of the Earth. Again, because we're on a sphere, no matter where you are, you're always the same distance from the center of the Earth, right? There's elevation changes, but those changes in elevation, if you go to the top of Mount Everest, that's very, very little distance change compared to the whole radius of the Earth, which is this really, really big sphere, right? And so if we're all always the same distance from the Earth, and downwards for us is always towards the center of the Earth, then we all experience the same pull downwards. And so we all basically just have the same experience of gravity. Now, this kind of leads to this picture where if something's directly in orbit around Earth, or any, gravitational object, well, it's not the only movement that's happening, right? Our Earth is orbiting around the sun, and our sun is orbiting around the center of our galaxy. And not only that, our galaxy is also shooting through space at some, crazy high speed. But we don't feel all of that compared to the feeling we have of the Earth's gravity. And so for all intents and purposes, if something's, near the Earth or orbiting around it, we can just kind of think of this system as the Earth as this just kind of static thing, and the thing circling around the Earth, right? All right, so now that we've got that taken care of, we can go back to galaxies and kind of test our understanding of gravity in them. So what this tells about our view of galaxies' gravity is that if we draw some sort of circle out from the center of the galaxy, well, we know that the two things that affect gravity are the mass and the distance from the center. If you draw that circle, no matter where you go on that circle, the amount of mass enclosed within that circle won't change. And also, no matter where you go on that circle, the distance from the center won't change. So since those two things that affect gravity don't change, any star that exists on that little circle you drew around the center of the galaxy is going to experience the same pull due to gravity, right? And so it stands to reason that if you drew some sort of different circle at some different distance from the center of the galaxy, then how much mass inside the orbit is going to change, and how far away is going to change, the distance. And depending on how these two things change, the force due to gravity will either increase or decrease. Does anybody have any questions thus far? Alrighty. So, well, these stars aren't just, standing there being pulled on by gravity. If they were static in the galaxy, then they'd be just pulled towards the center and they just fall into the center, right? No, they have to be orbiting around the center of the galaxy. And so no matter where the star is in this orbit, the force due to gravity is always going to be pulling it towards the center of the galaxy. Much like how if you're standing on the Earth, no matter where you walk, the force due to gravity is always pulling you towards the center of the Earth, right? And so for those of you who have taken physics, this red arrow, this V, just represents the velocity. So at any point, that is the direction it's wanting to move in. And then that green arrow is the acceleration, which we know, although it has a different value from the force, it points in the same direction as the force. So there's this force always pulling it inwards and its velocity moving it around in a circle. Now, if we're interested in the speed at which these stars are moving, then we need to know how it's affected by the force due to gravity. And what it turns out is that the speed at which these stars move is affected by the same two things that affect how strongly gravity pulls, namely the mass in the circle, the distance from the center. And what we're interested here for our little model is how does changing these two things affect the speed of the star in the orbit around the center of the galaxy, right? And so we know that if we have some sort of, spinning rope, if we pull harder on it, it's going to spin faster. That's pretty intuitive. And so for the first one, right, let's say we increase the mass within that circle. Well, increasing the mass, as we know, increases the force due to gravity. We increase the force due to gravity, pulls faster. So more mass is going to equal a faster speed. Now, the distance from the center is a little more complicated because we know that if we increase this distance, the force due to gravity is going to decrease. But we also know that it's harder to keep something moving in a circle when the radius is larger, right? It's way easier for me to do this than it is for me to do, this. I actually have to move it faster. I have to pull harder to keep it in a circle. But that's not an option, right? Because we know that increasing the distance from the center is going to decrease the force due to gravity. So it's farther out and it's pulling less. So the only other option is that the speed has to decrease because it's easier to keep something moving in a circle if it's at a lower speed, right? And so we increase the mass in the circle, we increase the force due to gravity. That results in an increase in the speed. We increase the distance from the center, we decrease the force due to gravity, the speed has to go down to compensate for that. I want you guys to just take a moment and look at this picture I've laid out for you. Does anybody have any questions about this picture or how changing either the mass or the distance will affect the speed of the star in orbit? All right. So moving on, we're getting to the math here. So all we really need are two equations. And the first equation, of course, is the force due to gravity, which you've probably seen in your introductory physics classes if you've taken one. Now, we know that the force due to gravity depends on gravitational constant, which never changes, big G. The big M being the mass of the object in the center, little m being the mass of the orbiting objects, and radius r being the distance between the two objects, right? So we increase one of the masses, that's numbers in the numerator, so that increases the force. We increase the distance, that number's in the denominator, so we decrease the force. Now, the other piece of our puzzle that we need is the centripetal force. We also know from physics that the force pointing towards the center of any circular motion, the force keeping it moving in that circle, has to be equal to this specific value, equal to, little m for the mass of the orbiting object, v for the speed of the orbiting object, the velocity, and r for the distance between the two objects, right? Now, we have these two equations, but if we look back here, we see that the gravity is always pointing towards the center of this orbit. Well, that's actually the exact definition of the centripetal force. The centripetal force is just the force that points towards the center of circular motion, keeping something moving in a circle, right? And so if these are the exact same force, that means we can just set them equal to each other. And this lets us just solve for whatever we want, right? And so from this point on, this is the only physics we actually needed to do. From now, it's just a matter of algebra, right? So we're going to go ahead and cancel out common factors. And then we have this v squared on the right side. So we're going to take the square root of both sides. And that lets us get to this final equation. Now you can see here that I wasn't actually lying to you. All that the velocity of a star in orbit or in the center of a galaxy depends on is this big G, unchanging gravitational constant, big M, mass in the center, mass enclosed within that circle, and little r, the radius. We increase big M, the mass in the center, we increase the velocity. We increase the radius, little r, because that number is the denominator, we decrease the velocity. And so let's take a look at our expected versus observed velocity curves now. So if we consider a star at some short distance from the center of the galaxy, well, that little circle it's orbiting around hasn't enclosed very much mass yet. There's a pretty small amount of mass enclosed there. And so likewise, the velocity is going to be relatively small. Now, you go a little bit further out, and we've now enclosed a lot more extra mass, but we haven't gone too far from the center that the decrease in velocity from that larger distance is going to overcompensate for that. So we have a relatively high velocity at these, intermediate distances. But then if we go out towards these far edges, the outer reaches of the galaxy, you can see that the material is less dense towards the edges. There's more stuff concentrated in the center of the galaxy than the edge. So if you go from these intermediate distances to the outside, you've increased your distance a lot, but you haven't increased your mass enclosed by a lot. So then that kind of results in this sort of characteristic drop off of the velocity as you go outwards, right? That's all well and fine, but when we take our telescopes, we point them towards galaxies in the sky, and we actually measure the speed at which those stars are going. What we see is, it kind of makes sense at these small and these intermediate distances. That matches up about with our understanding of what it should be. But at these really, really high distances, the stars are orbiting way faster than we would expect. And well, we know that the velocity that the stars are going at only depends on the mass enclosed and the distance from the center. We know the speed they're going at pretty well. We know the distance from the center pretty well. These two are kind of well measured numbers with low uncertainties. There's not a lot of things that could be messing with that. And so the only option is that there has to be more mass that we haven't found. There has to be some sort of invisible mass within these galaxies to account for this difference in speed, the higher speeds that we're seeing. And you can kind of visualize this as a sort of invisible dark cloud that that perpetuates throughout the galaxy. We tend to call them dark matter halos, although that's a little bit of a misnomer, like many things in astronomy, because they're not kind of a ring around the outside. They perpetuate throughout the entire galaxy. And you can see here in this picture, the dark matter halo extends way past the sort of visible extent of the galaxy, right? If we were actually looking at the galaxy, we might call the edge of it, where you can't really see any extra dust or stars like around here. But the dark matter halo goes much farther out. Now, one question that I had when I first learned about this, and one question some of you might have, is, okay, what if we just missed matter? I mean, that's not a silly question, right? There could easily be matter that's dark in the sense that it doesn't illuminate much, but it's still this, physical stuff, stars or black holes or gas or dust or whatever that we know exists. It's just not very bright, doesn't get lit up, and we miss it, And astronomers have wondered this And we've tried to test out to see if this can account for all the missing mass. We call these things machos because we love our silly acronyms, basically. Massive astrophysical compact halo objects. They've been proposed as a solution to this missing mass problem. Now, within these machos, you have black holes. Black holes don't illuminate much light. In fact, they don't illuminate any light, right? The only light that gets illuminated is from this kind of matter that swirls around the black hole, like you may have seen in this picture, taken pretty recently. The only light in this image is the gas that is orbiting around the black hole, emitting light that gets seen by us. You know, the actual black hole in the center of this gas is, you know, invisible, right? So if there's not a lot of stuff around the black hole, you can't see it. There's also brown dwarfs, white dwarfs, red dwarfs. Dwarfs are just these smaller, dimmer stars that don't fuse as much, and therefore they don't illuminate the stuff around them as much. And so we've looked for these things through a variety of different observational methods. And what we find is that they just don't add nearly enough mass that they can compensate for these flat velocity curves. One way we do this is through gravitational lensing. Now, much like how if you're looking at some object through a glass of water, that object will then become distorted to your eyes. If there's some large gravitational object in between you and some object you're looking at, well, we know that gravity can pull on light, right? And so light has to go into your eyes or go into, you know, a telescope or a detector and actually be processed and detected for us to see the object. So the background object might emit some light that then gets unnaturally kind of bent back towards into our eyes and our detectors, right? And this has the same effect as if we were looking at an object through water. The object gets distorted. Light that normally wouldn't reach us reaches us, and it creates this very characteristic distortion. Yeah, gravity can pull on light. It's a very, very small effect. Usually, right? Light moves so fast, and light has no mass. And so in the normal way we think about gravity, light shouldn't be able to be pulled on by gravity at all. But the normal way we think about gravity is generally a little bit of a simplification. And so on these really, really large, you know, giant, you know, large portion of the universe scales, light actually can be affected by gravity, but you would never know it if you were looking at something on the scale of, you know, our solar system. So dark matter is machos that can't be detected at all. No, not quite. So we find through our observations of machos here that we can actually tally up all of the mass of these objects that we previously might not have been able to detect. And to make things even better, white and red dwarfs are actually bright enough that we can detect them in significant amounts and kind of tally up the populations that we should be seeing. And they're completely ruled out, again, because we know at what rate they should be occurring in galaxies. And that is just not nearly enough mass to make up for these huge differences in the velocity curves, right? And so what we've done here is we've actually ruled out all objects that are made out of normal matter. And so it's not quite that it's machos that can't be detected. It's actually some sort of new exotic type of matter that doesn't make up all of these things that we know to exist and we know that we've seen before. It's something entirely new. That's the only option if these machos are ruled out, which in general they are. Let's see. So yeah, light is not light is not uniquely pulled by black holes. Black holes are, though, so massive compared to other objects of its size that it pulls in light, in an especially kind of dramatic way, right? You probably have heard that black holes are objects that are so massive that not even light can escape their gravitational pull. And that's a relatively accurate way of describing it, because any light that crosses that event horizon, they say that kind of radius around the black hole where nothing could escape, it's gone for good. It's just fallen into the black hole, and we're never seeing that light again. We can never regain the information from that light. So I am done with my kind of main slides here. Punchline here is that based on our understanding of basic gravitational and rotational physics, we can predict how fast these stars should be moving. If we do that and we compare them to the observations that we take of actual stars rotating around actual galaxies, we find that these actual stars are going way faster than we would expect. And the only solution to this, if we rule out all normal, typical matter as missing matter, is that there's some sort of exotic matter that doesn't interact with light, yet does interact gravitationally, that has to be in these galaxies, causing them to rotate faster than expected. So that was my main portion of my talk. I would like to stop here for questions. If anybody has any questions, please feel free to put them in chat about either the material here, the math, the physics, or just anything in general. In addition, if you guys would like for me to go to some supplementary slides that I've prepared, stuff that explains, for example, how we actually measure the velocities of these stars, then I'm happy to do that as well. Good question. Well, when we calculate the mass within, so first of all, this, just for bookkeeping, this big M is the mass of the central object that the thing is rotating around, and this little m, or orbiting around, and this little m is the mass of the object that's orbiting around them. Now, we know from gravity that, we know in the case of gravity that these two masses are kind of interchangeable in the sense that both of these need to experience the same force due to gravity. But then over on this side, we know that the centripetal force depends specifically on the mass of the object that's doing the orbiting. Now, the heart of your question comes from the fact that we're kind of making a little bit of an oversimplification here when we talk about gravity, right? So if you imagine this, this Earth right here to be kind of the equivalent of that little, whatever little circle you draw around the center of the galaxy. Well, if we know everything experiences gravity, then this little guy right here, he's not just being pulled on to the center of the Earth, like alone. This guy is being pulled on by, Maryland up here, and he's also being pulled on by California over here, and he's also being pulled on, whatever, by China all the way on the other side of the Earth. He's being pulled on by all these different parts of Earth individually. But the Earth is a sphere. So let's say we draw some line right here that divides the Earth equally into two little half spheres. Well, there's about as much matter on this left half sphere as there is on this right half sphere, right? And so if you're being pulled the same amount to the left as you are to the right, then that component of being pulled, then those two components cancel out. And what you are left with is just being pulled basically to the center, right? So, if all of these things cancel out, then we can kind of just pretend that the Earth is just this infinitesimally small little piece of mass here at the very center of the Earth. That's not what it actually is, but these people's experience of gravity is going to be the same whether that's true or not, right? And so what that lets us say is that all of these stars and gas and dust, everything within this circle, the same way all of the different pieces of the Earth, amount to being pulled to the center of the Earth, all of this stuff just amounts to an equivalent mass right at the center. Hopefully that answered your question. Whoa. Sorry if you guys heard that. It just started storming out. What about the gravity of a non-spherical object? Well, you kind of would have to analyze it on an individual basis. I will admit that we do make simplifications here. Some galaxies are not perfectly spherical shaped, plenty of them aren't. If you were working with a non-spherical object, what you would probably do is try to find the symmetries that you can. It would be the same if, for example, it was, a square. Anything that you're outside of, as long as it's symmetric, you're still going to be pulled to the center of it. As long as you get pulled the same amount to the right as you are to the left, then those two right and left components are going to be canceled out and you're not going to be pulled right or left at all. But luckily, most things in the universe are close enough to spherical that we can just kind of pretend they are for most applications. A lot of the times when you're doing stuff like that, it comes down to, how much can you simplify and still get the right answer? And luckily for a problem like this, we can typically simplify a lot. Why is it important to be studying this? It's fascinating, but still. Well, I will say, first of all, that fascination is kind of its own value. I think that this is definitely an open area of discussion, and there are many contentious opinions about this. But my personal viewpoint is that knowledge for knowledge's sake is honestly a good thing. There's a lot we can learn about ourselves and the world around us by just seeking information about things that interest us. But luckily for us, the pursuit of astronomy actually is a very useful one. The most obvious thing I would mention is all of the theory, the math, and the physics that we develop to describe astronomical objects, or the strategies and the techniques we use in computer simulations to simulate astronomical objects. All of those have really rich applications in plenty of other industries. Not to mention the actual experimental side of it, right? When we build a telescope, we have to go through a lot of processes of like very fine machining, putting the mirrors in the right spot, assembling and manufacturing everything. We have to develop these really complicated computer algorithms to analyze images and figure out what's in them and create kind of rigorous conclusions from the information in the image. So astronomy, because it's such a technical and quantitative discipline, it has a lot of leak over into other industries that tend to really pay for itself, honestly. Not to mention that, well, there's kind of this ripple effect going on here, right? We're talking about galaxies, but there are stars in galaxies and planets orbit around stars, right? So if the galaxies were different, then the stars would probably be different and the planets would be different. And so this kind of overarching meta discussion about this, astrophysical neighborhood that we live in actually helps us kind of constrain things about what it might be like to live on another planet, or what it might be like for another species in another area of the universe. And so there are many different offshoots, many different kind of interactions between this kind of knowledge and other kinds of knowledge, basically. Other than the lack of alignment with expected star velocities, are there other signs that dark matter exists? Yeah. This is part of my supplementary slide, so I'm going to go down to over here. So another strong piece of evidence comes from clusters of galaxies, right? We were talking about that whole spherical approximation thing, right? If you think of then the galaxy as its own little ball, then a galaxy has a really strong gravitational pull on other galaxies near it. And so galaxies will tend to pull on each other and then settle into these groups of galaxies that are orbiting around each other that we call a cluster. Now, we can honestly just play the same game that we were playing before and measure the velocities of these galaxies themselves within the cluster, right? And well, a similar analysis to the one we just did holds. And so we can play the same kind of velocity curve, expected versus observed game with whole galaxy clusters. We can also use gravitational lensing, like I was just talking about, to directly measure the mass of galaxies or galaxy clusters. And this is mass that is going to include the dark matter. And so that'll basically just give us a measurement for the actual mass. And then we can compare that to the mass we get from visual light-based observations. There's also a lot of kind of hot diffuse gas that exists in these galaxy clusters, and this gas emits light in the X-ray region of the electromagnetic spectrum. And when it does that, it gives us information about the temperature of the gas. If we have information about the temperature of the gas, we can use that to deduce information about the pressure of the gas. And while we know about these galaxy clusters that pressure has to push out as much as gravity pulls in, right? Because if pressure is pushing out more, then these galaxy clusters these galaxies in the cluster are all going to be pushed outwards, and it's no longer going to be settled. If gravity is pulling in more than pressure pushes out, then all of these galaxies are going to spiral into the center, and they're all going to merge in to become one galaxy, right? So if it's a stable cluster, pressure has to be pushing out as much as gravity is pushing in. And that information lets us deduce, again, the force due to gravity. And in general, these different measurements typically agree on the general scale of the amount of mass that we need to add for our theory to agree with the experiments. Just measuring the mass of the galaxy seems much more simpler than calculating the velocity. Well, I would then ask you, how do you measure the mass of the galaxy without, putting it on a scale? There's no super easy way of doing that. We can't reach out and grab the galaxy and, put it on our instruments. From observations, so are you talking, for example, gravitational lensing? The problem with gravitational lensing is you need an object in between us and the observed object, or rather, you need a background object to get lensed by this object that you want to measure the mass of, right? So we don't get to control the environment of our universe, the things just kind of exist as they are. And depending on kind of the situation, the environment, where the galaxy is in relation to other galaxies, how close it is, how strong the light is we get from it, all these different kinds of factors. Sometimes one measurement is going to give us a much more accurate or trustable result than another. And let's say that we can get accurate results from both kinds of measurements. Well, that's actually really good. We want to do both because in science, we're playing a game of, trying to test our theory. And so doing a measurement two different ways will increase our confidence a bunch. So it's actually a really good deal that we get to be able to do it in multiple ways, even if one is a little bit more difficult or complicated. I want to do my undergrad in mechanical engineering, but I have a fascination with astronomy. Do you know of a way for me to study both, some kind of crossover? Yes, Instrumentation, man. Oh, I'm sorry. I did not see your name. Instrumentation, ma'am. Yeah, no, Instrumentation is definitely your best bet. The instruments we use to actually make these observations are really complicated, and they have to be really, really precise. There's a lot of really interesting engineering that has to go into the actual creation of telescopes, of the kind of telescope systems, the domes and the gears and all that stuff that actually, houses the telescopes and makes them work for us. If you're talking about spectroscopy, which is something that I can get into a little bit later in my supplementary slides if you all want. Spectroscopy is a field that requires very specific, precise instrumentation. Spectroscopy just amounts to basically putting our light in through a prism and letting it kind of split into its component wavelengths, right? Because white light is made out of many different wavelengths of light, red, blue, green, whatever. And what we do with spectroscopy is we actually split out this white light into so that all the different colors of light go in their own directions, and we can measure how much of each different color of light we get. And that's actually how we measure velocities, which I can get into a little bit later if you all want that. Are things in our galaxy orbiting in more of a circular orbit or more of an ellipse? Technically an ellipse, but very, very close to a circle. It's, it's definitely closer to a circle than like a really fat ellipse. And we can do this kind of analysis using the math that describes ellipses rather than describes a circle. But oftentimes it's close enough to a circle that we can do this analysis and get good results. And also it helps kind of demonstrates the concepts much clearer. I've never sat down and done the math on pen and paper with an ellipse, but I've done this little game with setting the gravity equal to the centripetal force many times. Any thoughts on the hypothetical planet 9? Well, I'm not entirely sure which exact one you're referring to. The thing about planets is that there are tens of thousands, maybe hundreds of thousands of objects orbiting around our sun, from tiny little pebbles to giant planets the size of Jupiter, right? Nature does not care about our distinctions of what's a planet, what's an asteroid, what's a comet. There are many things that are almost planets, they're almost the right size. And so, well, what we need to do with defining a planet is make the definition actually work for us, right? It has to be a classification that's actually useful. And our classification that we call a planet tends to result in a lot of things that are almost a planet, but not quite, because they don't clear out their orbit. That's one of the qualifications for a planet. A planet needs to be able to clear out its orbit of any other little things that are nearby orbiting around it. And so there are many other objects that are around the size of Pluto that if you wanted to, you could almost call a planet. If you want to, if it makes you happy and helps you sleep at night, then feel free to. I actually don't know about the specific object you're talking about, but we are always getting newer, even more precise measurements of the way these objects are orbiting around our sun in the solar system. And oftentimes we do find anomalies in the data that lead us to believe that there's some other objects gravitationally influencing the other objects in our solar system in a way previously not thought. So it's totally possible that there's some sort of hidden extra object, some hidden object, maybe even the size of Pluto or Aries or anything of the like. Will the slides/recording be sent out? I'd love to see more of the supplemental slides. For sure, I can send the slides in chat. And when I get the recording, if you guys are interested, I can totally, if I'm able to and everybody's interested, I can totally send out the recording to that large mass email when I get it. I'm happy to do that. Oh, I'm sorry. Yes, the recording will be available on YouTube soon. Awesome. Thanks so much. Could we measure the gravitational pull of the planets in the solar system using the velocity method to get better proof of dark matter? So you are right. We can get way better. That's a good thought. We can get way better measurements on the velocities and the masses of objects in our solar system, right? We can get real low uncertainties on that. The problem is dark matter is not nearly dense enough that we actually have a significant enough amount of dark matter contained within our solar system for it to really affect the motion of these objects that much. Like there's a lot of dark matter in our galaxy, right? But our solar system is just one tiny, tiny little neighborhood of that galaxy. And so in terms of effects that we could actually measure, it's not thought that there's enough dark matter around that it really affects gravitationally the scale of our solar system. The increased accuracy wouldn't be enough to show a slight difference. No, unfortunately not. There's also, there's the problem that dark matter kind of forms structures on the scale of a galaxy, right? So dark matter is going to be more, there's going to be more dark matter towards the center of the galaxy, less dark matter towards the edge, right? There's going to be some sort of density profile of this dark matter. And that density profile, it is going to change as we go kind of, radially outwards from the center of the galaxy. And the only way we would be able to measure, the only way we'd be able to measure the effect of dark matter on our solar system is if that density profile changed appreciably on the scale of our solar system. So like the distance, from one end of Kuiper belt to the other end of the Kuiper belt, the diameter of the Kuiper belt. If the density of dark matter changed significantly from one end to the other, then we would be able to measure some sort of difference. But without that, because it's so much less abundant than other stuff around us, we just can't really we can't really measure its effects, unfortunately. Now, there are experiments that people have been doing for the last few decades on Earth to try and measure dark matter as it just kind of passes through us, right? Because we know that dark matter has to be very weakly interacting. We know that dark matter doesn't interact electromagnetically. We know that the two ways. Thank you for the heads up. We know that the two ways matter can interact with itself or each other is through the electroweak force, the strong force, electromagnetism, weak force, strong force. This all this stuff we kind of bunch up together that we've all kind of married together in our idea of how this thing called particle physics works. So we've got this theory over there, and then we've kind of got gravity over here doing its own thing. So for our purposes, let's say just things can interact electromagnetically and gravitationally. Well, we know that dark matter will not interact electromagnetically with things, with the kind of things that make up our normal everyday matter, my computer and myself and my desk and all that stuff. We know it'll interact gravitationally because we know it has this effect on the galaxy rotation curves. What dark matter will do is probably, based on our kind of theories, our mathematical models of what we think of how we think it works, it'll typically just pass right through us uninterrupted and then just go on its merry way. We do think that dark matter should, perchance, if it's lucky enough to run into certain types of particles that it can interact with, it should be able to kind of show that. And there are some experiments that have been done over the past few decades where we basically just get a giant tank of some sort of gas. The one I'm familiar with used xenon gas, but there are many, many of these giant international collaborations trying to do this. Take a giant tank of xenon gas and they just measure it, and they hope that eventually a dark matter particle is going to pass through it, interact with it, and it'll show up on a detector that this dark matter particle passed through, and they have actual observable, detectable evidence of dark matter. We've been trying to do this for decades, and we've made a lot of progress, on the technical realm, on the theoretical realm, but it's starting to get kind of sketchy. Like there's really no other way to put it. We have many a time thought we were going to see dark matter and didn't see dark matter. And so this honestly remains to be one of the biggest, most interesting unsolved problems in physics, right? We have so much evidence from the astronomers of what dark matter should be like, how much there should be of it. And we have some general ideas from other realms of physics like cosmology, what some of the actual physical properties of the dark matter particles should be. Then we go out and try and measure it, and we don't find anything. And so there's a lot of interesting work that remains to be done here. And yeah, still a lot of questions. So let me go ahead and, while you guys think of some more questions, just real quick, show you how we actually measure velocities. So you may have heard of the Doppler shift effect, where it's, as the ambulance, as the siren of an ambulance, for example, comes towards you, you've probably noticed that it sounds higher pitch as it's moving towards you, then as the ambulance starts moving away from you, it sounds lower pitch. This comes from an effect where the observed wavelength emitted by a moving object changes because of the fact that it's moving, right? We know that sound is made up of waves. And so if this ambulance is emitting the peak of a wavelength, whatever, at some constant interval, then as it's moving forward, those peaks are going to like catch up with each other. And so what that ends up causing is an apparent shortening of the wavelength of the ambulance siren, right? And we know that shorter wavelengths correspond with higher pitches and that longer wavelengths correspond with lower pitches. Well, you may have heard before that light also travels as a wave. And so light can also experience the Doppler effect. And so if an object is moving away from us and it emits some light, we're going to see that light as being a lower wavelength than we originally expected. If it's moving towards us and it emits light, we're going to see that light as having a higher wavelength than we initially expected. I'm sorry, I said that backwards. Longer wavelength as it's moving away from us, shorter wavelength as it's moving towards us, right? And so we know from the electromagnetic spectrum that red has a longer wavelength and blue has a shorter wavelength. So we call the experience of seeing a longer wavelength red shifting. We call the experience of seeing a shorter wavelength blue shifting. Now, we got these stars orbiting in these galaxies real fast around the center, right? So let's say we're looking at one of these spiral galaxies so that the edge, we see just the edge. Does that make stars look different colors? Yes, it actually makes them look different colors. Now, the Doppler shift, the effect wouldn't be so drastic, probably, on stars that are close enough we could see them with the naked eye that we would actually see them as like looking a different color. But this effect happens on galaxies too, right? Because galaxies are also moving through space. And this is actually something really cool that if you take a picture of a galaxy with a small redshift and you take a picture with smaller redshifts and you take pictures of galaxies with larger redshifts, you can actually see, if you look at like a whole bunch of them, you can actually see the trend of them looking more red, literally to our eyes, if you take a picture of them. So yes, it actually causes our experience of seeing them to change. Now, if we look at these stars moving around in these edge-on spiral galaxies, well, let's say they're orbiting in, this direction, right? So if these stars on this right side over here are moving towards us, then they're going to be blue shifted on that side. And if these stars on this left side over here are moving away from us, then they're going to be red shifted, right? And so we know what wavelengths of light these stars should emit because we know what they're made out of and we know the chemical interactions that happen within these stars. And so if we just measure the wavelengths at which they emit, then we can just work backwards, knowing the wavelength they're supposed to emit at, and calculate the velocity of these stars from that information. And we do this by using this, prism-like instrument that kind of separates the light into its component wavelengths and puts them onto a detector where we can measure at each wavelength how much light did we get. Alrighty, does anybody have any final questions? All right, well, in that case, thank you all so much for for being very participatory. You all have been great. I hope you've learned something. Thank you guys.